go to the next floor.
Fine. This might be the most fair.
No way.
Right.
No, you're not wrong.
No experience in the work field, I would agree. Yeah, but from someone who's been in the field for at least 12 years, I can tell you,
No, I understand.
that is completely normal.
I get your point.
I rescind most of what I said.
You have to be panicking that once again, we don't have.
Yeah, that is good.
Oh, we're back at it again with them cameras.
Oh, yeah.
With what?
The cameras, the video calls.
No polling.
No polling.
Per usual.
Pretty damn classic.
This cord is gonna be.
And this is my weekly call to say
You
that
should get up.
I have this in Bremerton, but I don't have the Pullman section. The class started
Get
a
up
minute
and
ago.
we have fun.
No.
All right, thank you. It's taking control.
He just hangs around campus.
Gotcha.
Okay, so once again, I think we're kind of in a holding pattern until Pullman gets online. Which hopefully will be soon.
They're always late, aren't they?
Not always.
I don't think.
A lot.
they are late.
But I don't think it's them.
Yeah.
I don't think it's them. I
Students
think
of
it's
like-
like
Whoever
whoever
began the call.
online classes. Oh,
Like that
oh,
person,
there.
like that person in red, maybe.
Alright, alright, so I guess I'll start with Bremerton. Bremerton, can you hear me all right, and are you seeing content? Alright, give this a thumbs up, right? And Pullman, can you hear me, and are you seeing the content?
Yeah.
Excellent. Alright, well, let's get going. Alright, so what I wanna do today, my plan for this week, we'll see how it goes. My plan for the week is to more or less finish up the aerodynamics of horizontal axis wind turbines today. Basically everything except the last section or two of chapter 3. On Friday, I'd like to demonstrate Q blade to you guys. I'm also going to release the project on Friday. And depending on how the Q blade demo goes, I don't know if it will take the whole 75 minutes. Maybe we'll also talk about the project. The project is a group project. I'll probably create some like class participation type assignment where you have to just get on campus and let me know who your partners in the project will be. I'm hoping for groups of 3. There can be groups of 2. There should not be groups of 1, and there should not be groups of 4. I don't see any reason why people on different campuses can't work together, although it might make things more difficult. To get back to what we've been talking about, I kind of want to like refresh your memory everything we've done in this chapter so far. The first thing we did was we started with basic one-dimensional momentum theory, and I derived the Betz limit for you. And in deriving the Betz limit, we came up with this very important value A, which is our induction factors. Essentially the amount of the velocity of the wind is slowed down as it approaches the wind turbine. Then we did momentum theory, but including the concept the wake behind our turbine is going to be rotating. And in doing so, we introduced this other induction factor, A prime, which relates the rotational speed of the wind behind the turbine, in the wake of the turbine, and compares that to the rotational velocity of the turbine itself. Also in doing that, we developed some nice forms for the amount of thrust on a blade caused by a particular angular ring around the rotor, and also a differential torque. And then I introduced you to some airfoil and aerodynamics basics, kind of aerodynamics 101. And once we did that, then we could combine the aerodynamic theory about the forces that are acting on our wings or airfoil blades. And we can relate that to the thrust and the torque that we found from momentum theory. And that did 2 things for us. One, it gave us some formulas that we can use to design an ideal airfoil shape or an ideal rotor shape for our wind turbine. And so far, we've only done that without assuming that the wake behind our wind turbine is rotating. Later today, we'll do this again, but we'll come up with some formulas that do consider rotating wake. And then finally, we were also able to, for any given wind turbine rotor design, whether it is in ideal airfoil shape or not, to, under conditions that may or may not be the ideal conditions that it was designed for, we now have a methodology for performance prediction that is finding the amount of power or the percentage of power or our power coefficient. Maybe I'll just write here, we can now find CP for a given airfoil design at a given tip speed ratio. Okay? And so today we're going to put all this together. Before I do that, I do want to kind of repeat some of the things that I talked about on Friday, because I don't feel I covered it in a good amount of detail, and I kind of was rushed at the last 10-15 minutes of class. So if you'll bear with me, I'm going to repeat a little bit of what I talked about at the end of class on Friday. So the main thing I wanted to talk about was this off-design performance. And I do feel that I do remember that I covered this, but I was watching the video, which is posted on YouTube already. And I didn't actually see where I talked about some of the details of this. So the issue is that we have this beam element theory. We have this blade element momentum theory, and it involves taking our momentum theory and equating it with our blade element theory. But if my induction factor A is greater than 0.5, my momentum theory is not valid. And so we can't use this method. So it was proposed by Gallart that he found that when your induction factor, that is when the velocity, your turbine is spinning so fast that the wind, as it hits the rotor, slows down so much that it actually slows down to more than half, less than half its mean flow velocity, or its free stream velocity. Which, remember, that's what this induction factor is how much the wind slows down. Okay? So Gallart proposed this equation where he relates the induction factor A to what he called the thrust coefficient, or what's called the thrust coefficient. The equation he came up with was 0.143 plus the square root of 0.0203 minus 0.64, and I know I wrote this equation down, 7 times 0.889 minus CT, where CT is what's called the thrust coefficient. And it's CT for a particular radius. And this is, it's the normal force, so the thrust, divided by 1/2 rho u infinity squared, and an area which will be 2 pi r dr. Okay, so it plays the same role as the lift coefficient or the drag coefficient, but this is the thrust. So you can find the thrust, or you can, by taking this number and multiplying it by this denominator. Okay, so if you have this, then you can equate this thrust that you find with this with equation 8. So from equation 8 prime, in blade element theory, BET is blade element theory, then I can find that CTR is equal to the local solidity, all right, 1 minus the induction factor squared times our lift coefficient times the cosine of the angle our rotor makes with the relative wind velocity, plus CD times sine of the angle our rotor makes with the relative wind velocity. All this divided by sine squared of the angle our rotor makes with the relative wind velocity. And I called this, so in my notes, I call this equation number 21, and I call this equation number 22. Okay, and I know so far I'm repeating myself. All right, so I gave you guys an iterative procedure. This is the part I don't remember saying in my in lecture. Is what we do is we modify our iterative approach. So I'm going to modify our iterative approach like this. So one, I start as always. By guessing A and A prime. And I just keep going until after I find updated alpha CL lift coefficient, drag coefficient. Then I'm going to use equation number 22 to find my thrust coefficient for R, the thrust coefficient for this particular radius, for this particular element. And 3, this is where the modification occurs. If this CTR is, I should do this in green. If this CTR is less than 0.96, I just continue as normal. But if it's greater than 0.96, then I'm going to use equation 21, which I just derived, to update my next my next value of A, to update my induction factor. And I know you'll have to look at your past notes, but 18A can be used to update. All right, and one of the things I know I didn't show you is the nice thing about Gallard's empirical relation is that if my angular induction factor is less than 0.5, so 0.5 is right here, this Gallard's empirical relation is going to give us pretty much the same thrust that we would expect if our that we would get from our normal approach. But it diverges and gives us more accurate results if our induction factor was greater than 0.5. Remember, if our induction factor is greater than 0.5, this dotted line is meaningless. Okay, and we would expect, I mean, this makes sense, right? If our wind turbine is spinning so fast that it's essentially acting as a disk and wind can't even go through it because it's rotating so fast that the wind just has to go around it, then we would expect our thrust to be getting higher, right? We expect the wind pushing against our rotor to be higher, not to start going down again. And if we use the methods that we normally do, if we use our regular iterative method, we'd be getting results that are meaningless. Okay. I then listed off, and I was really rushed, and I listed off a bunch of other issues. And the first one was if we're using the graphical method, which I don't encourage you to use. Remember, this is a graph where we're graphing our angle attack versus our lift coefficient. And our airfoil polars are going to look like this. And equation number 14 is going to look it could look something like this, and under certain conditions, they'll cross twice, which means you can't use this method. Or you can use this method, you just have to be a little bit more clever. Okay? So that was one issue I mentioned, and then just as the camera shut off, I started pointing out that we've done this all analysis, but this analysis is a model, and we made a good number of assumptions. And so we have not considered certain things that affect real wind turbines. Okay, so we have not considered wind shear. That is the wind at the bottom of your turbine. If this is my rotor, my hand is my rotor. The wind at the bottom of my turbine is likely likely flowing at a slower velocity than the wind at the top. Okay? We have not considered yaw error. That is, we're assuming that, again, if this is my rotor, the wind is blowing perfectly normal to the rotor, and that the rotor isn't turned the wrong way. Okay? So we haven't considered yaw error. We haven't considered the vertical component of the wind. So if this piece of paper is the ground, I've been assuming that the wind is blowing, and I guess this is the tower of my wind turbine. We've been assuming the wind is blowing perfectly horizontally. It could be blowing either like this, or it could be blowing like this. We haven't considered turbulence. And I think the students have ever heard me talk about this. I don't think the students on the other campuses heard me say this is just as the camera. We haven't considered what's called blade coning. Now I'm going to talk more about blade coning probably the week after next when we start talking about mechanics and dynamics. But you have a wind turbine. Let's say, actually, let me go drop it. So I have a tower, and then I have my wind turbine blades in front of my tower. The wind's blowing, and these blades are not perfectly rigid. They've got some flexibility to them. So either when the wind starts blowing really hard, they're going to rotate back. And so they don't actually exist. We've been modeling our rotor as a perfect plane. That everything exists in a perfect plane. But in reality, your rotor is going to be bent. Now, sometimes the blades are actually designed so that when the wind is not blowing, they are purposely coned away from the rotor, away from the tower, so that when they bend back, they don't hit the tower, which would be bad. All right, so a lot of these issues discussed here are more or less outside the scope of this class, the models that we're going to be discussing in this class. Some of these we'll discuss later, but we're not going to develop more detailed mathematical models than we already have. I think you'd agree with me that the model we've developed so far, pretty mathematically complex for an undergraduate level class. We're really right at the border of what I would consider, all right, we're kind of getting into like maybe a grad level class here. I think what we have in here, what we've done is doable. Okay? And you do have a homework assignment I posted Sunday, I think, that's due, I don't remember, but like in a week and a half, I think. And I think the homework assignment's doable. Okay? If you look at it and you don't feel it's doable, and you don't know where to start, email me. Come to my office hours. My office hours are virtual. If you look at the syllabus, I have a Zoom link for my office hours. And they've been really quiet this semester, which is great for me to catch up on extra work, but it's not really what office hours are used for. All right, one other thing I want to talk about, and then we're going to go over an overall picture. Yes, so let's very quickly talk about how we can improve our formulas for blade shape for optimal rotor, but now we're going to consider wake rotation. This is going to be really quick. All right, so this is blade shape for optimal rotor. With wake rotation considered. All right. So now we have the tools. We have the tools now. To find our blade angle. This is remember, phi is the angle our rotor makes with the relative wing velocity as a function of r. And from here, we can find our blade twist or our pitch as a function, our blade pitch as a function of r. And we can also find our chord length, our ideal chord length as a function of r, with considering our weight is rotating. The way we're going to do that is, so this equation, which in my notes is equation 19 prime, this equation is Cp, so they don't expect you to memorize it. This is the speed ratio at the hub. That is the tip speed ratio, and the equation was sine phi of cosine phi minus lambda r sine phi times sine phi plus lambda r cosine phi. I got it from here. 1 minus our ratio of our drag coefficient over our lift coefficient, cotangent phi lambda r squared, and I'm running out of room, but d lambda r. This was equation 19 prime. What we're going to do is we're going to just take this part of it, which is the part that really involves and minimizes and maximizes, particularly if we assume that drag is really small. This is the part of the equation that involves phi. And what we're going to do, we're just going to take this, because remember, we're trying to optimize our power coefficient. Okay? So what we're going to do, which is whenever I want to optimize something, I'm going to take the derivative of this with respect to phi, and I'm going to set it equal to 0. And then I'm going to solve for phi. Okay? So what I'm going to do is I'm going to say the derivative with respect to phi of, and don't worry, I'm not asking you guys to do it, of sine squared phi cosine phi minus lambda r sine phi times sine phi plus lambda r cosine phi. I'm going to set that equal to, and I'm going to set it equal to 0, and then solve for phi. And what I'm going to get is that phi is equal to 2/3 the the inverse tangent of 1 over my local speed ratio, and also from another equation that allows me to derive that my ideal chord length is 8 pi r over b, remember b is the number of blades, our lift coefficient, times 1 minus cosine of b. Put a big red box around those two equations. All right. These are the equations that you use for your ideal pitch and your ideal chord length. And remember, this isn't your pitch, this is your angle that you make with the relative velocity. And remember that this angle, B, is equal to your pitch angle plus alpha. And you know alpha because you decided what alpha is going to give you your best results based on your studies of airfoil floors. Okay, so you know alpha. Once you know this, you can find the pitch. All right. Now it might be interesting, and I think I'm just going to do this. So yes, when I did not consider the wake rotation, these are the two equations I came up with. So these are the equations for my notes. I think these might already be posted. And as you can see, they're very similar equations. Okay. But these will give you a more accurate result. If your tip speed ratio is really high, then your wake rotation will be small, and you'll get closer to these values. Okay, but you can use either, depending on the situation. All right. Now I'm going to put everything together. The big picture. And this is probably going to take us most of the rest of the class. Yeah. All right. So, new topic. And this is our generalized design procedure. And you're gonna want to take good notes. You're gonna want to pay attention because, as what may not be a big surprise to you, your project is going to be to design a rotor, right? So I'm going to give you certain wind conditions and a certain, like, we want it to produce this much power, and we want it to produce this much power, and I might give you a wind speed. It's going to be built or designed to operate at a location with a given wind speed. And this is the procedure you're going to want to follow. Okay? So, step 1, determine the power and energy needed and the wind available at the site of interest. You can use this equation that our power is equal to our power coefficient times the efficiency of our gear system times 1/2 rho pi r squared, r being capital R being the rotor, and our velocity cubed. You can make a reasonable guess of things like you don't know your power coefficient, and you don't necessarily know how efficient your generator is, but maybe you can look that up, or maybe you have a generator in mind that you plan to use. And you can use this to estimate R. how big a rotor do you need to get the power that you want? That's step one. Step two, choose a tip speed ratio. If your goal is to do mechanical work, you might choose a tip speed ratio between 1 and 3. So this might be for like pumping water. For electrical power, usually somewhere between 4 and 10 for electrical generation. And about 7 is common. Three, choose your number of blades. And 3 is common. If lambda is less than 3, you really don't need airfoils. You can just use curved plates. And, if you look at, the typical wind turbine that you see on a old farm, they just had curved plates, right? They were designed to maximize torque. If lambda is greater than 3, choose an airfoil or family of airfoils. And then you want to do some research. So you want to obtain and study the airfoil pullers. And you can use this using, and I don't expect you guys to do this, you can use Xfoil, which is an application, it's an open source application that will give you those airfoil pullers. What I recommend that you guys do is you do some research using airfoiltools.com. And I believe I've already linked. I've posted a link to this on Canvas under class resources. If I haven't, then let me know and I'll put that link there. All right. So for each section of your blade, you're going to choose an alpha. You're going to choose your angle of attack. And you're going to choose it so that is the location where your drag coefficient, your ratio of your drag coefficient to your lift coefficient is minimized. Usually it's around 7 degrees-ish, 7 to 8 degrees. That is the angle of attack that you want to pick for your airfoil. Now, you're going to design your blade is not necessarily going to have one airfoil shape. So you're going to design your blade. So this is step 5. Step 6. Is you're going to divide your blade into we're gonna say N, capital N elements. Or strips. Or stripes. Typically, somewhere between 10 and 20 is enough. All right, so if that's your airfoil blade, and this is the hub, you're gonna break it into strips. Now, each one of these strips could be the same basic airfoil shape, or they could be different. You have to design it. You do want to design it so that it can support its own weight. We're going to talk about forces and things like that, and some of the structural stuff in the coming weeks. But for now, just use your best judgment. You can't have it too thin at the, so typically you have it thicker towards the center, and it becomes thinner. Okay? And you might consider things like, hey, I want my airfoil, I want my rotor to generate a lot of torque when the wind's not blowing very hard, because it needs to start. Okay, so what you might do is design something where you have a particularly high torque at the tips, because you'll not only have more tangential force, but you also have a longer arm. Okay. Probably that's also going to be where you're going to generate most of your power, so you don't want to put too much there. You want to think about these things, okay? So you will make different decisions based on you may make different decisions based on what you're trying to do, okay? So you might decide to use, like, I don't know, I'm just throwing these names out, but you might use like an ACA 2412 during certain segments. You may decide, okay, I'm going to use a NASA 52871 for a different, further out, okay? The choices you're going to make for your strips, though, are not necessarily like, oh, you're going to make, this is going to be one airfoil shape, this is going to be another airfoil shape, this is going to be another airfoil shape. This division here is for your analysis. You want to have enough N elements that if you're using a different airfoil shape during part of your rotor than your other part, that you would have enough N elements so that each element is more or less one constant airfoil shape. Okay? All right. So, now what you're going to do, this is still part of 6, is you're going to use your optimal rotor theory to estimate a shape of each ith element. So we're going to call some arbitrary element the ith element. And what you're going to have to do is you're going to have to do the same analysis over and over again for each element, for each strip. Okay? So for each ith element, where this is I equals 1, and this is I equals n, you're going to use optimal rotor theory to estimate ideal shape of the ith element. And just to be clear, I equals 1 is at the hub. Okay? All right. So those formulas are, you first need to calculate your lambda, your local speed ratio. So lambda Ri, remember that is equal to the radius I. So this distance here is Ri, divided by R, capital R, times the tip speed ratio, which you picked up. I did not want to write that subscript. Sorry. Remember earlier you picked what your lambda was, your tip speed ratio. So this is your tip speed ratio, this is your local speed ratio. So once you have that, then you can use the formulas that I just showed you to come up with that our relative wind direction is going to be 2/3 the inverse tangent of 1 over lambda Ri, and that our ideal chord for this element or this strip is going to be 8 pi Ri divided by B times CL, because you'll know the lift coefficient that you want. So this is your design lift coefficient. This is the ith, and this is 1 minus cosine of phi I. Now, once you have this, you can then find the pitch of the ith element, because you know that this is going to be this phi minus your alpha that you designed for the ith element. You can also find the blade twist, which is the pitch that you just found the ith element, minus, if you do this element first, this outer element first, that is going to be the pitch 0 in the book. It really should be pitch n, because it's the pitch of this nth element. Okay? All right, now, I decided this right before class. I don't have the neatest handwriting when I'm being rushed, and there's a lot of math here. So I just want to also clarify, cross-reference this with the book. This is equation 3.110, 111, 12, 13, and 14, okay? So that's step 6. So step 7 is you're going to use step 6 as a guide. But select blade shapes that can be manufactured. Okay, and can withstand likely loads and fatigue. Right, and this is going to be, for now, this is going to be just use your best judgment, right? Like, obviously, your chord length near the hub can't be so large that the blades are crossing each other and hitting each other, and you want to have some, use your best judgment for now. We're going to cover some of these issues like fatigue and loads later in the course. Step 8, we're going to use the methods, and we're going to review them here, and I'm going to put them all together in just a few minutes. So we're going to use methods discussed to predict blade performance. Now, if you look in the book on page 135, they cover the graphical method. But I'm going to skip this. And I'm skipping because if you're going to write a computer program, you're not going to use this method. And we have computers, so we might as well use them. All right, so everything I'm about to write on page, on my next page is part of 8. Okay, so I'm going to continue with step 8, and I'm going to walk you through the entire procedure, and I'm going to give you every single equation that you need. Okay, so we're going to iterate through each blade element. And we're going to use I for our ith element. And we're going to use an iterative approach to find things like, alpha I, CLI, and so forth. And so when in this iteration, I'm iterating twice. Yeah.
Would it be feasible to iterate for lambda, like tip speed ratio? Or is there too much decisions we make based on that to kind of keep going back?
I'm not 100% sure I understand your question, but if I understand your question correctly, okay, so first off, we are in a sense iterating through lambda I, right? So we're going each element we're iterating through element I, or you could say we're iterating through local speed ratio I. However,
I'm talking about lambda overall.
You're talking about lambda overall.
Yeah.
Then yes.
Okay.
What we're going to do is first do this. So everything, step 8 is first we're going to do this at the design.
Yeah.
This is the tip speed ratio we're designing for.
Okay.
And then.
And you go back.
And then now let's do it for a range of tip speed ratios, going from 0 to whatever tip speed ratio results in 0 power. I hadn't gotten to that.
Okay. Oh yeah. Okay.
Does that say,
so,
I have a question.
Yeah.
Does it say through pieces blade element?
Through each.
Okay.
Wait, what did you think it said?
Can you zoom in a little bit?
It's either pieces or peaches. I wasn't sure.
Oh, it's peaches.
Because that makes a
Oh,
lot
that's
of
not
sense.
a peak. Dude.
You're gonna get a Presidents of the United States of America song stuck in my head.
Yeah.
All right.
Oh.
All right. So J, we're gonna use J through our So we're gonna for now our outside iterator is I and our inside iterator is J. Okay. So this is step 8.1. We're going to guess initial values of AI0 and A prime I0. And we can just always start with AI 0 being 1/3, which is our optimal value. Or we can, if we're on the ith element and I is equal to 1, we could start with, okay, what was A for the element, for the bladed strip just adjacent to this that we just found. Okay? But for now, let's just say we're getting the guess values of A and A prime. Remember, this is my induction factor and this is my angular induction factor. And then we're going to update what we can use, or we can use. Okay, so then 8.2, after we made our guess, is we're gonna use all those equations that we just covered. So, and I'm gonna give you the equation numbers in the book as well. So we're gonna find our tangent of our pitch angle, ij, is equal to 1 minus a I comma j over 1 plus a prime I comma j
When you have a 348 test in the morning.
times lambda r I. If we are concerned with tip losses, we'll find f, and f is equal to 2 over pi times the inverse cosine of our exponential times minus b, that's the number of blades, over 2 times 1 minus ri over capital R, that's where we are along the blade, divided by ri divided by capital R, sine of e, which we just found, of I comma j. I know this is messy. This is equation in our textbook. This is equation in our textbook 3.127, and this is 3.128. I can then find my true, remember that my true alpha, I comma j, is equal to b, I comma j, which we just found, minus our pitch.
Is that Fi comma j?
And I can adjust CL comma I and CD comma I based on polars. It's really IJ. All right, so I want to be clear on this. When we were designing our blade, we got to pick what alpha was. But now we're on an off design, so our alpha might not be what we want it to be. Our angle of attack might not be what we want it to be. Particularly if we're working on a lambda, that's not our design.
I have a question.
Yeah.
Is that Fi comma j or Fi comma s?
That's J.
Okay. Dude. Thank you.
I don't know if that made it look more like a J or more like a blob of ink, but.
No, that's good.
Okay. This is equation 3.129, or yeah, 3.129. Okay, now we can find our thrust coefficient. And again, this is for I comma j. So it's a local thrust coefficient for this, at this iteration. And this is equal to solidity at I. So our local solidity, 1 minus a ij squared. The local coefficient that we just found, the lift coefficient that we just found, cosine e I comma j, plus our drag coefficient, I comma j, sine of e I comma j, over sine squared of e I comma j. This is equation 3.130. Now, as we just covered, if where's my color? CTR I comma j is less than 0.96, then I will set a I comma j plus 1, because now I'm updating my iteration, so I'm coming up with a new induction factor, is equal to 1 over 1 plus 4 f ij, I just derived that, sine squared of e I comma j divided by my local solidity I, which I'm not solving for, so that's a constant within this iteration for this element, or this strip, CL I comma j, cosine p I comma j. This is equation 3.131. Now, if CT, if this statement's not true, then the alternative is true. And then I use that, I use this Gallard's formula. So then A I j plus 1 is equal to 1 over f I j times 0.143 plus the square root of 0.0203 plus, no, I'm sorry, minus. Minus 0.6427 times 0.889 minus CT R I comma j. Okay, and this is equation in the textbook 3.132. All right, the only thing I have left to do, and I don't quite have room on this page, maybe I'll put it.
Wait.
Are you good?
Yeah.
No.
Okay. All right, so now I need to find A prime. Well, I don't think you realized there was about to like move, yeah, you ripped it off so I could move it up so you can still see the water. Right? The last thing.
Damn.
All right, so we need to find our angular induction factor, I j plus 1, which is equal to 1 over 4 f I comma j cosine p I comma j.
That's probably right later.
minus divided by our solidity CLI comma J. And actually, this is all minus 1. This is equation 3.133. Okay, and then iterate. So continue iterating until AI comma J is approximately equal to AI comma J plus 1. And A prime I comma J is approximately equal to A prime I comma J plus 1. And you're going to do this for all I. Okay, so then once you're done with that, you're done with your iteration. And all of this was 8. Okay, this was all step 8. Step 9. Yeah.
Is that 3.132 equation, or I'm sorry, 3.133 equation applicable to both? And it's,
Yes. Yes. Let me repeat the question. So we have this, if our thrust ratio is greater than or less than 0.096, and that is only for calculating the axial induction factor. Regardless of the value of our thrust factor, we use this equation to find our angular induction factor. All right. All of that was step 8. So step 9 is to calculate our overall power coefficient. So we're going to calculate CP. And to do that, I'm going to use this formula. CP, and I've written this formula before, but I wrote it before as an integral. Now, this is a real numerical technique. I'm going to write this as a summation. So summing from I equals 1 to n, we're going to calculate 8 delta lambda r, I'll explain what that is in a second, over our tip speed ratio squared times Fi sine squared Bi cosine Bi minus lambda r I sine Bi times, and I'm putting a times here and I'm continuing on the next line, sine Bi plus lambda r I cosine Bi times 1 minus, my brain got ahead of myself.
So that's
Our
minus.
ratio. Give me 1 second. I heard there was a question, but give me 1 second.
Okay.
Okay, I'm sorry, what was it? I'm done writing. What was the question?
It's the first line minus the second line?
No, that's a.
Yeah, okay.
That's a dot. Okay. And again, this is, look, I'm handwriting equations. In the textbook, this is 3.134. Okay, and it's a really good idea for you to double check my equation. Oh, I need to explain what this is. This is just the difference between our two local speed ratio, so delta lambda r, I should probably say I, is equal to lambda r comma I minus lambda r comma I minus 1. Okay, so it's just like what we're doing is essentially we're integrating over our, here, I'll do this as an aside. Remember, we were integrating from our tip speed ratio to whatever our tip speed ratio was at the hub. And all of this was inside this integral. And what we're doing is we're just coming up with, well, we didn't really divide it into a infinite number of infinitely small delta lambdas. We're just going to take 10 or 20 strips and approximate. Okay? And so when we approximate, we have to deal with the fact that our d lambda r is actually a finite value. So we need to multiply each of these strips with this value, or with that delta, to get our full power coefficient. So now we find our power coefficient. Yay! All right, now step 10, because Dan wanted to do this.
Thank you.
Step 10 is repeat everything. And remember, you're not repeating anything, okay? You're not doing it. In the old days, like, you would have come up with the algorithm, or you would have written the algorithm in some, well, quite frankly, some undergrad math did. But you're not doing this. Your computer, right? You're going to write a computer. And by the way, this step of doing everything, of working this up, is probably going to be like an extra credit part of the assignment of the project, okay? Now, step 10, repeat everything. But basically repeat steps 6 through 9. For, yeah, I don't think I need this. For, how did I say this? For, I'll say a variety of lambdas, of tip speed ratios. Say from lambda equals 0. You don't have to do it at lambda equals 0 because everything will be 0. All the way up to, and I'll explain what this is in a second, lambda runaway. Okay, so you're going to have another loop on the outside of your step 6 through 9 loop. Okay, that's just going to say, okay, you did this first for a specific lambda that you thought, based on your design, this is the lambda I'm designing around. What you want to do is you want to create a plot that looks like this. So you're going to create a plot where this is lambda, and this is a power coefficient. And the first time you did this for your lambda design. So this is the lambda that you designed for, and our steps 6 through 9 was to find this value. And you were able to say, okay, this is my power coefficient. So you've now been able to say, like, this is what I predict the percent of power available in the wind that this rotor will convert to mechanical energy. What you need to do now is do this again. You don't have to do it at an infinite number of values. But what you're going to find is close to, well, at 0, tip speed ratio is 0, I guarantee you're not going to be producing any power. Because, physics. If you've done everything correctly, and you probably haven't, because remember you started with this ideal rotor shape, and then you had to make a bunch of compromises for the fact that it actually has to be able to support itself, it actually has to be manufacturable. So it's possible that your optimal, that the design that you, the tip speed ratio that you designed for might not be your largest value. But what's likely to happen is you'll get a curve that looks like this. So when I say up to your runaway ratio, your lambda tip speed ratio runaway, that's here. This is your lambda runaway. This is the tip speed ratio that what will happen is if your rotor becomes disconnected for some reason from your generator or your brake stops working and your rotor starts and the wind speed is very high, what will happen is there won't be any resistance against your rotor. And at some point, the wind is going to cause your rotor to spin around as fast as it can at that wind speed. And at that wind speed, that's your runaway tip speed ratio. So basically, you just want to go, you want to repeat everything from some number close to 0 up until you find that CP is we basically reduce back down to 0. And then you're done. And oh wow, that's a really good
There's no
place
way
to
to
stop.
stop this thing.
Okay, that's a really good place to stop. I actually have like a page and a half left of notes and some other just like minor issues, but we can cover that. Yeah, I'll cover that really quickly on Friday before we do the cube blade demo. Hey, by the way, this is Wednesday of week 7, so we're halfway done with the semester. Literally, yeah.
What?
It's hump day of the semester.
Yeah, they wouldn't be able to run it and like have it do.
Not a very good.
Add some outputs for certain.
Yeah.
I have them. Picking groups.
Still working on
So I don't know before it's ever decided so.
which is kind of funny.
See you later.
Thank you.
Yeah. No problem. I read that whole thing like, no, I need to catch up on 3 lectures now.
Dude,
Well, because remember, no, because I missed.
computer science.
Oh, so, okay.
Class?
We'll be in touch.
Did I actually have your number?
That's a good point.
I think I already have my notes, so.
Very good.
Are you in 122?
No. Really? Hell yeah, I did.
I want to be
No,
I'm not-
come
no,
on.
no, I'm not gonna, because you know.
Wow, I fucking did it. 17, What did you, wait, let me show you. Let's go back. He did? That's how he did.
See you guys.
Hi.
Over 100.
Yeah. I think it's the 10. That's what I did. Yeah, the
I'm thinking
16
we make
one
a
was like
nice-
really off. I mean, it was like,
two things.
it was weird.
One,
So I used 10.
your nice big brain equation.
Because it says that this
You
was
run
the
it
max,
down,
but it only had this current.
Two, maybe.
So like I just assumed like, okay, I'm gonna do 10 because I don't know the current and I don't know where we are.
Yeah.
So if we're over 2, then our max would still be 10.
Yeah.
So
And then, okay, so you did that, you pretty much just like broke down all the other percentages that you found.
Yeah, and then I just used whatever.
So you didn't use any of those 10 data.
Mostly I'm just hungry and I.
That's how you do the inverted signal thing.
Well, I didn't. So.
And you still get a 9.9 there.
Right,
how, no, all that
You know what,
stuff
I'm
is
so tired of
check,
all
make
these
sure
boys
that
complaining about being a girl, being a girl, this much, what do you know?
You're done? Nice. Nice.
And after that, the first thing I'm gonna do is take that waterproof spray and treat these cats, because they, let's just say if we were in the Arctic, I would do that. That's my barometer for choosing cold weather clothing.
Ah,
Can I survive?
See you later.
see you later.
All right, sweet.
I feel like we're gonna be bad group members. We have to make sure not to be bad group members.
Yeah. I'm pretty sure we have a rep. I think our biggest flaw, honestly, is just that we talk too much and get into side conversations. Yeah. So, I mean, as long as we stay focused on the task.
Mm-hmm. That just means we shouldn't be telling like, what's the word? Just inside jokes around him.
Oh, yeah.
That's the main thing.
Yeah.
It's inside jokes that we can all get at the moment.
Yeah.
I'm not worried about the project.
Yeah. No, and that's one of the reasons why I asked her is because she.
Did she help you in computer science?
Yeah. Well, no, we work together a lot in labs because we're in the same group bunch, so I know her.
Oh, nice.
But I mean, I just noticed that she's often sitting here by herself.
Good job.
So I figure if
Good excuse to include her.
also I just realized I'm going to be putting my hood on, so no sense in strapping up the helmet yet. But it is 5:34.